All right. So, as always, I need someone to confirm our existence. But before we do, Avi, I think you and I have one really big disagreement that I think we need to get to the bottom of first, which is the name of the galaxy when Andromeda and the Milky Way merge.
Right. Well, about a decade ago, I wrote a paper about it, and I was thinking about the merger product for a while, for 2 decades, and I convinced a colleague of mine, a postdoc, to work on that and simulate the future.
Yep.
And in fact, as we wrote the paper, we talked about this merger remnant multiple times, and I realized that it would make sense to give it a name. And so I thought of combining Milky Way and Andromeda into Milkomeda.
Yeah.
And I checked the web and there was nothing. So I used it as a convenient term. It saved us space in the paper. So what do we disagree on?
So hold on. So you went with milk. I thought, was it Milkomedia or Milkdromeda?
Milkomeda.
Yeah. See, so there it is. Sorry, people are saying my microphone is the wrong mic, so I'm just fixing this. And let me switch this around. Yeah. So Milkdromeda is the
Milkomeda.
one.
Yes. Milkomeda. Another way.
Milkomedia. Yeah. No. See, that's it. So I think we are going to disagree. But that's okay. I think we can.
It's just a name, It doesn't.
It doesn't really matter. No.
Yeah, I mean, the interesting point is that within a few billion years, while the sun is still alive, this merger will take place. The night sky will change. Instead of seeing the stars distributed in a thin layer that we call the Milky Way, they will be spread all over the sky because the merger product will be an elliptical galaxy, a galaxy that looks more like a football rather than a disk. And so that will be with us for a while because all the other galaxies will run away from us at an accelerated pace. They will move faster and faster with time. And eventually we will lose sight of those other galaxies because of the accelerated expansion of the universe. So we'll be left within Milkomeda, surrounded by vacuum. And that's a gloomy future for extragalactic observers. But in principle, we can avoid that future if we only develop spacecrafts that will take us out of the galaxy into the nearest cluster of galaxies. The amount of resources would be 1,000 times bigger over there because it's a group. The Coma cluster, for example, is 1,000 times the mass of the Milky Way. So we will have many more stars over there if we wanted to use them for anything. We'll have many more neighbors if there are any extragalactic civilizations. So, it could be the next cosmic engineering project to propel ourselves into the nearest cluster, because otherwise we will be left in this galaxy, and that will be it.
Yeah. Well, I mean, so before we get into all of these ideas, I just want to give you the quick introduction because people may wonder who you are and what you do. I'm an enormous fan, but let people know who you are and what you do, and then I will continue to sing your praises.
Sure. My name is Avi Loeb, and I'm the Frank B. Baird Professor of Science at Harvard University. In terms of my administrative duties, I chair the astronomy department at Harvard, and I'm also the director of 2 centers there. One is the Black Hole Initiative. It's the only center in the world that focuses on the study of black holes, and it brings together philosophers, astronomers, mathematicians, and physicists that ordinarily speak different languages, but when they discuss black holes, they come together at this center. And Stephen Hawking came for the inauguration a couple of years ago. Then there is another center called the Institute for Theory and Computation, which is very broad in all aspects of theoretical astrophysics, and I'm the director of that as well. I'm also the chair of the board on physics and astronomy of the National Academies, and the chair of the advisory board for the Starshot project. Right. Is a project to visit the nearest stars.
And I know a lot of people are going to have a bunch of questions about that. I do too as well. But I like to think of you as like the hardest working person in astrophysics. It's funny. So, I mean, my regular day job is that I'm a journalist. I'm the publisher of Universe Today, and I'm constantly looking for interesting stories for us to publish on Universe Today. And I'm always going through the AstroPH listing of all of the new papers, and every single time I see a paper, I'm like, oh, that's such a cool idea. Okay, we're going to report on this. And then I look at the name like, oh, it's Avi Loeb again. Okay. You have done so, I don't know how you keep up the publishing schedule of all of the papers. I know you have a great team that you work with and a lot of co-authors, which makes sense. But you just in the last year, I think, we've reported on stories from you about just how many icy worlds there are out there in the universe, the habitability of those icy worlds. You worked on simulations for the Event Horizon Telescope. You've calculated how long the universe would be habitable shortly after the Big Bang. You are involved in the Breakthrough Starshot. Like, I could just go on and on and on. And then you talked about this in the introduction, right? That we are going to potentially be able to move stars around in the far, far future to make them more organized for our purposes. So, before we get into these individual stories, like, what's your productivity secret? How do you publish so much?
Well, I don't see myself as very special, you know. I mean, I have ideas that seem to me quite natural and down to earth and sort of straightforward. And what I'm surprised by is that others did not think about it before. So, you know, when I speak to a plumber that comes to fix the sewer, we had a flood in our basement. You know, I speak with that plumber, and then it occurred to me that, you know, the fact that water collected in the basement reminded me of matter collecting at the singularity of a black hole, and of the fact that we don't speak enough about this singularity. And where does this matter collect? You know, what is this singularity? And it led me to think about it as a quantum object, you know, that a place where matter collects at the center of a black hole. So all of these things, you know, and people come to me, young people come to tell me about what they do. And it often, you know, occurs to me that there is something trivial they should have thought about. And I mention it to them, and they say, oh, wow, this is really cool. This is an interesting idea. Let's work on it. This would be quite exciting. And what is surprising to me is that they haven't thought about it in the first place, because, you know, and I'm quite different from most astronomers. I was not driven to astronomy or science early on. I was mostly interested in philosophy, the big questions. And so I'm quite different. And it's just, it's unclear to me why other people don't think about these things. So I don't think about myself as special. What occurs to me is that it's the surprise that others did not think about all of these. And when I see they haven't thought about it, I write about it. So, you know, right. That's it.
So at least somebody did. Yeah. All right. Well, so let's move through some of the ideas. And I know people are going to have a bunch of questions for you as well. And I think the one that has caught almost everyone's attention and imagination is this idea of the Breakthrough Starshot. So can you give people just a quick idea of how this is going to work?
Yes. So the question that was posed to me by Yuri Milna, the funder of this project that is quite visionary, he said he thinks that it would be extremely exciting to visit the nearest star. And he asked me to look into the technology that would allow us to do that. And I looked at it with my students and postdocs for about 6 months and reported back to him. And I told him basically that, you know, fortunately, there is one method that looks practical, but it's just like getting married. You only need one solution to your problem. It doesn't be more than one. So we are very fortunate to have that solution. And basically, there is a fundamental limitation to the rocket approach that we use for all of the space missions so far, because in that approach, you carry the fuel with you. And as the fuel burns up and you throw it through the exhaust, the burnt gases, you still need to accelerate the rest of the fuel with you before you burn it. And so that limits your speed to be just a multiple, a factor up to a factor of 10 bigger than the escape speed, the speed by which the exhaust ejects the fuel. It's sort of like a jet plane. It's the same principle. You just get the boost from throwing stuff backwards. And you just can't speed up much more than the speed by which you throw stuff backwards. And that's usually a speed much less than the speed of light. Now, the nearest star to us is 4.25 light years away. It means that it takes light 4 years and 3 months to reach us. So if there is an intelligent civilization out there that is looking through a giant telescope at us, they are just aware of the Obama era. Yep. They're not, because Trump was elected just less than a couple of years ago, and it takes 4 years for the light to traverse that distance. So if it takes light 4 years and you want to accomplish this mission within our lifetime, then the spacecraft better move at least 1/10 of the speed of light. And you can't do that with rockets. In fact, you can't even do that with nuclear engines, I figured. And the only way that seems in principle doable with present day technology is leaving the fuel behind, not carrying the fuel with you, and using light for propulsion. In other words, just like a sailboat is being pushed by wind, we can use light to push on a sail. And this concept is not new. Soon after the laser was invented, Robert Ford, back in the early 1960s, thought about this idea. The thing that happened since then, since the 1960s, is that two technologies evolved dramatically and reached maturity. One is lasers. It's now possible to combine laser beams that are relatively low power into a more powerful beam. And the laser cost is much less. It drops with time. It follows roughly a Moore's law. And the second is nanotechnology, the fact that we have a miniaturization of electronics in cell phones, for example. And that allows you to construct a spacecraft that weighs only a few grams, that carries a camera, a navigation device, a communication device. And since it's so light, you can, in principle, push it with a very powerful laser up to a fraction of the speed of light. And that was the concept that we came up with. We worked on it for several months with Yuri, iterated with him, and then assembled a committee, a board that includes distinguished physicists. And the next phase, Yuri committed $100 million for feasibility study. So the next 5 to 10 years will be dedicated to demonstrating the feasibility of the technology using experiments, laboratory experiments. We selected about 12 teams that will do experiments relevant for the demonstration of the laser. And we are also selecting right now about 12 teams that will do experiments related to the sail. You need the sail to be very lightweight and also sturdy, very strong. And the shape of the sail is to be determined. It needs to be stable. It needs to ride on the beam of the laser in a stable fashion. And so we are working on this feasibility study. If it is successful, if it's promising, we'll move on to the next phase, which will be a demo, a prototype system that will demonstrate this concept. And eventually we'll move on to the final construction. So each phase will be a factor of 10 or so in cost. And the ultimate cost of the system is estimated to be roughly like the Large Hadron Collider or the James Webb Space Telescope, the biggest science projects that are funded right now. But it would be quite exciting if we can actually reach the stars. Mm-hmm. You might ask, well, could it be that another civilization did that already? And it's quite possible. We would have a hard time noticing such a small spacecraft crossing across, the sky, because it moves so fast and it's so small. It doesn't reflect much sunlight. But I should say that there was an object that came from interstellar space.
Sure, Oumuamua.
Oumuamua, yes. Yeah. And that was quite peculiar. This object was very elongated, more than any other asteroid that we found in the solar system. It was roughly half a mile in size. And the other thing is that it didn't really follow the orbit that we expect based on the law of gravity around the sun. It seems to deviate a bit from it. And it's not at all clear why, because it doesn't have a cometary tail.
Yeah.
We don't see a cometary. So actually, I suggested we discussed it with Yuri and decided to check if it has any radio transmission. Maybe it is artificial. Turned out that you can put a limit with existing radio telescopes. You can put a limit of up to a tenth of a cell phone.
Yeah, that's what I'd heard. If you were on Oumuamua and you were on a cell phone, the radio telescopes would have heard you. They would have detected.
Which is amazing if you think about it. A single cell phone at the distance of Jupiter or so.
Yeah,
you can detect that.
Now, I've got a couple of questions for you. Our audience is we've talked about this several times. They're definitely on top of the science on this. One of the questions that keeps coming back and back is, I totally understand the idea of sending a lot of these probes to, send thousands if you need to. They're small, inexpensive. How could you, but the transmission is going to be one of the most difficult challenges. How are you going to be able to get a signal back to Earth? We have, there's a lot of spacecraft now. One of the, like New Horizons can just barely send a transmission back to Earth, even though it has an RTG on board. It has a pretty good communication system. What ideas have you put together to be able to actually get these pictures of other stars back home?
Well, this is an excellent question. But first, I should say the target may not be just the nearest star. The nearest star system is Alpha Centauri, and it has 3 stars in it. One of them is Proxima Centauri that has a habitable planet, which is tidally locked to it and could potentially, it's in the habitable zone of Proxima Centauri. So this planet could potentially have life. And indeed, we would like to take photos of that planet to see if it's green, whether it has vegetation, blue, whether it has oceans, or maybe it's a desert. And then for that, we want to fly by and take some photographs, as you say, and transmit them. That would be a great challenge, as you say. We estimated that in principle, if you open up an antenna of the size of the height of a person, roughly, at that distance of 4 light years, you could potentially transmit enough radio signal, or it could be infrared signal, to detect it with a big enough telescope on Earth. But it's not trivial, it's not easy, as you say. And we went through the numbers. It is doable. I should also mention that to reach Pluto, for example, will take a few days rather than almost a decade as it took New Horizons. So if there is an object of interest in the solar system, for example, Oumuamua that we just discussed, is running away from us faster than any chemical rocket, so we cannot chase it. But if we had the technology of Starshot, we would easily catch up with it and fly by, take some photos. We would get more information. Right now, we don't know what it looks like. Is it artificial or natural?
And so, I was thinking that maybe you'd utilize some kind of daisy chain to try and have send probes on a regular basis, and they could somehow send the photos and information back along the chain.
That's a possibility, but it doesn't save much. It turns out that it's a possibility to have relay stations along the way. You're right, but turns out that it is possible in principle to construct a strong enough signal. We're talking about sending the signal with a laser, for example, from the spacecraft that has roughly 1 watt of energy power.
And so just the bigger the listening you can create, the bigger the telescope. Say you turned the entire Event Horizon telescope on Alpha Centauri or on Proxima Centauri when the probes are getting there and trying to transmit back, then that means a smaller transmitter, and then that makes sense. I'll be able to use that as an answer in the future. The other thing, and this feels more like a publicity, not stunt exactly, but you just talked about it briefly, that Oumuamua would be an ideal target. The reality is that there are 100,000 fascinating targets right here in the solar system. Every single moon, every single planet, every single dwarf planet, every single asteroid. Those are absolutely fascinating targets that astronomers would beg to have any close-up photographs and spectroscopic information of.
I agree.
That feels like it's the natural target
Yes.
for these missions for the foreseeable future until we've mastered the intricacies of it and then send them to another star. So isn't that really where these things are going to go? Is everywhere in the solar system?
That's definitely that's an excellent point. There are two reasons why such a technology would be appealing. One is that the travel time is much shorter, as we discussed. Instead of a decade to get to Pluto, it could take a few days.
Yeah.
And the second is that these are cheap spacecrafts. So since they weigh only a few grams and they are made of technologies that are similar to a cell phone, we're talking about the cost of hundreds of dollars per spacecraft. It's not very expensive. And so the fact that it's relatively easy to reproduce such a spacecraft makes the project, the launch of such a spacecraft much easier. It's not a huge mission like we operate in the spirit of the way we operate right now, where you have to plan for a decade and then it takes another decade to construct this mission and so forth. Here it will be, once we have the infrastructure, it should be really straightforward. Whenever you identify an interesting target, you just send that direction.
I can imagine some space-based manufacturing 3D printer that just prints out new spacecraft, and there's a queue like the Hubble Space Telescope, right? You just get your destination request in the queue, and then whenever your turn comes up, the next probe that comes out is sent off to your target, and a couple of days later, you get the data that you want.
Yeah, and you don't worry so much about one of these spacecrafts getting destroyed as a result of a collision with an asteroid or a dust particle or whatever, because it's not very expensive. So you can send a collection of those in the right. And also, if you worry about not being precise, if you send a few of those around the region of interest, that should cover it. So yes, now there was an article in Forbes magazine that appeared a week ago arguing that, if there is an alien civilization out there, it might see such a technology as an act of war.
Right.
But I actually wrote a reply to that should appear shortly.
Yeah.
In which I explained that there is nothing to fear about because the amount of energy carried by such a spacecraft is comparable to the energy carried by an asteroid that is roughly the size of a human. And we have such an asteroid, there are a few of those every year that they hit the atmosphere and they burn up. And here we're talking about a spacecraft that weighs only a few grams, so it will burn up much more easily than a few meters size asteroid. These things are more similar to the irritation that a grazing cow would feel from a dust grain hitting its skin, than anything else. So there wouldn't be much of a concern about a risk for another planet and also the chance of hitting a planet would be extremely small because we aim to be within a few thousand times the size of the planet to take the photographs. And the chance of hitting the planet directly would be 1 in a million or less. So this is really not something to worry about. My hope is that once we reach the interstellar highway, obviously I have no fear that we will be fined for speeding or that there will be any road rage. I think it's more likely that we will receive a message saying, welcome to the interstellar club.
Yeah. Your probe was destroyed, but welcome to the club.
And there must be I don't think we are likely to be alone. I think that what we see around, just out of modesty, I think the life that we see here on Earth must be replicated in many other places. And so my guess is that we are not the first ones to think about interstellar travel. Yeah. And that the most so we keep thinking about looking for life and looking for intelligent civilizations on planets near stars. But my guess is that the most common, the most abundant signatures of such civilizations would be flying objects that fill up the interstellar medium. And they're quite small, so it's not easy to detect them, but I'm sure they are out there.
So one of the other issues, of course, is attempting to slow down, and I think this is not a deal breaker. I mean, if you can't make these spacecraft slow down, you got your pictures and the spacecraft flew through this other star system, and that's great. But in an ideal world, you would be able to slow these spacecraft down. Have there been some ideas on ways that you could slow them down again to go into orbit and maybe stick around?
Well, in principle, if you launch them at a slower speed, then it should be possible to slow them down on the radiation from the star, or if if you send a low-speed spacecraft such that it lands on the target planet, let's say, and then you can build there the infrastructure that was used to launch these things. Then you can imagine the reverse, having a parachute on these things that's with a laser over there that slows them down. It's just that we don't have equivalent system out there.
Right. Once we had some kind of infrastructure, you could imagine this future transportation system where lasers are accelerating from the sun, lasers are decelerating from Alpha Centauri, and you've got this way of getting around.
Right. And I should say humans are not designed to interstellar space. So, science fiction movies show humans traveling, but these are very long journeys. And it's true that if you accelerate a human for a year at 1g, which is the acceleration we feel here on Earth, then it will reach the speed of light. But that requires a huge amount of energy to get there. Right. And otherwise, the journey will take more than a human lifetime. And if you don't reach a fraction of the speed of light, and so, and there is no reason to risk the lives of people that we care about. All you need is to send a 3D printer that carries the information of how to reconstruct the human out there, and reconstruct it. And I think electronics or machine learning, artificial intelligence are really the future. And so eventually we'll be able to basically have the information that encapsulates our existence transferred rather than ourselves.
I'm seeing a bunch of questions coming from the audience now. A couple of questions that I think are interesting. One, Mr. Tommy Pickles asks, what kind of a camera could we fit on such a craft? What kinds of photographs? How many photos will you get as one of your spacecraft is flying through another solar system?
Well, think of the camera as similar to that we have on a cell phone. Basically, we can take photographs of that quality, and the camera will weigh less than a gram, a fraction of a gram. And in principle, if you want higher resolution, then you need a bigger lens. But the calculations we have done were for that type of a camera that you find in a cell phone. And the number of photographs that you can transfer is dependent only on the communication device, on how fast, how much information you can transmit per second. And that depends on, as we discussed before, on the means of communication. So if you use a laser, that limits the number of bits that you can transfer. And so roughly we're talking about the photographs every few hours or so, if you take realistic numbers, and not much faster than that.
And you will have passed through the solar system within a couple of days, so you're only going to get a few dozen photographs.
Well, that's if you visit a target in the solar system. But if you go to the Proxima Centauri planet, for example, then you could take a lot of photographs, store them in memory, and then relay them over a long period of time. And it takes 4 years for these photos to reach us. So, and we can't correct the course of this spacecraft because it's already out there.
And I guess, that's how New Horizons worked, right? That it took all of its pictures over the course of a day, and then has been transmitting those photographs back for the better part of 18 months. It just finished, and now it's about to do this again, and then we're going to have to wait even longer for the next series of images. So that makes a ton of sense.
Now, if we were to send New Horizons, it would take 100,000 years to reach Centauri. So So the point is that, if you are willing to wait long enough, you can send something that will move slowly and eventually land. But, if you think 100,000 years ago, that's when humans started to use tools in Africa. A lot has happened since then. I'm not sure we want to wait 100,000 years. And the other thing is, once we launch something that will take 100,000 years, within those 100,000 years, we'll develop technologies that will allow us to do much better, and we will overtake that spacecraft. So there is no point in doing that.
Well, one thing is great as well, though. The Parker Solar Probe, with how fast it's going to do its mission to the sun, it'll only take 6,000 years. So just keep that in mind, that now humans have the technology. We've knocked like a factor of 10 off that flight time. So now you'd only need a generation ship that would last for a ridiculous amount of time. So another question here, this came from Arjone. I know, went back here. Could a laser highway be constructed in the solar system using these types of lasers? And so this is a conversation that I've had many times on my channel, is this idea of infrastructure in our own solar system. And these lasers sound like they would be one of the most efficient, effective ways to be able to just help spacecraft move from world to world within the solar system itself.
Right. Yes, so every long journey starts with the first step, but indeed you can think about the subsequent steps that will be taken. And obviously we could move first to the moon and then to Mars and so forth. And it makes a lot of sense, for example, to have a transportation system between Earth and Mars, for example. You don't need to move at the fraction of the speed of light for that. It can be transportation that moves things at less than 1% of the speed of light, and faster than chemical rockets, but not very fast. And that, instead of using a laser in the infrared or wavelength range, you can use a radio a maser, so-called, at radio wavelengths, millimeter or centimeter long wavelengths, the type that you find in a microwave oven. And those are optimal, actually, for launching things between Earth and Mars. And we went actually through the numbers. And the interesting point is that if you imagine a similar system already in existence in another planetary system, where you have a pair of an Earth and a Mars planets among which there is a transportation system, then every now and then you will see the beam of radiation that is leaking outside the sails, scanning the sky, and you will see it as a flash of radiation. And an interesting search to make is for flashes of radiation that you would see from a planetary system as a result. Now, as it turns out, there are fast radio bursts. These are flashes of radio transmission that we receive from space. Again, most astronomers would tell you that it's quite likely to originate from neutron stars, natural sources, at cosmological distances, but it could be that a fraction of those are associated with such systems.
Yeah, one of the best tools for finding this is actually here in Canada at the Chime Observatory.
That's right.
Yeah, which is this really, it's a little far, a few hundred kilometers away from where I live on Vancouver Island, but I definitely want to go and take a look at it.
And one thing I should say is the search for extraterrestrial intelligence is considered outside the mainstream for some reason that is not clear to me, because we are talking about a phenomenon that we find here on Earth, okay? And we know that a quarter of all the stars in the galaxy have habitable planets around them. We know that from the Kepler satellite. And so all that one is saying is that, if conditions are similar on other planets, a quarter of the stars may have such planets, then we should search for a phenomenon that we find here on Earth. That makes a lot of sense. It should be mainstream. I don't see anything speculative about it. So it's a sociology of science that is unusual. And because at the same time, you have people, theoretical physicists, talking about extra dimensions that are curled up and we can't see any evidence for them.
Yeah.
And that is considered mainstream. And to me, it's the other way around. I mean, I would think that searching for intelligence in the sky is more of a mainstream activity than searching for extra dimensions.
I absolutely agree with you. It is perhaps the most fundamental scientific question that a human being can ask is, are we alone in the universe? And anyone who thinks that it's not an interesting question, I would, if I knew the answer, I could write it on a piece of paper, I could put it in an envelope, and I could give it to them, and I could say the answer is in there. Would you like to open that envelope? Are you curious to know the answer? It is a scientific question. One thing that was really fascinating, we actually talked to Brad Peterson, who's working with the LUVOIR telescope just 2 weeks ago, and he said something really interesting, is that LUVOIR, when built, will know with 90% accuracy if we're alone in the universe. It will help us find. It'll be so capable at analyzing the biosignatures in the atmospheres of other worlds that we'll know to a certain radius out there whether or not we are alone, which I think is really fascinating.
So that's correct, but that's the search for primitive life, for signatures of molecules in the atmospheres of planets, and that is within the mainstream. And just recently, about a couple of weeks ago, we wrote a paper with a postdoc of mine, Manas Villingam, where we estimated the likelihood of success in the search for primitive life, meaning looking for molecules that are indicative of life, like oxygen or methane in the atmospheres of planet that could be produced by microbes, versus the chance of success in a search for intelligent life. And we concluded, based on all the information we have, that it would make sense, given that we have these ambitions to build these big telescopes that will cost billions of dollars, that it would make sense to invest about 1% or so of that money in the search for intelligent life, because the chance of success is roughly 1 in 100. And searching for intelligence makes sense at the same time as searching for primitive life. And if we search for molecules that are indicative of primitive life, we could also find industrial pollution, for example, in the atmospheres of other planets. It might indicate not so intelligent life, but industrial life.
Right.
Or it could indicate that there are aliens out there trying to change the climate artificially, because if the planet is too cold otherwise, you might introduce these gases into the atmosphere that warm it up.
Now, one of the things that you've also done a lot of the math on is this idea that there are potentially 1,000 times as many water worlds as there are terrestrial planets. So planets like Earth in the habitable zone where life can form, there are potentially 1,000 times as many worlds, because we see places like Europa and Enceladus and potentially Pluto and Eris and all of these places out there could have life as well. But they are difficult places for life to get very complicated, and especially for us to even be able to detect it. So
that's right.
Can you talk a bit about that, just about sort of that idea?
So there are many more objects where you have an icy surface under which there is a liquid ocean. And that's simply because of the properties of water, that the ice could potentially protect the inner region. And so you could have liquid water under the surface, and that liquid water could potentially be in contact with rock, the way that it is on the surface of the Earth. And the advantage of that is that first you have, as you said, many more such worlds, but also that you are not restricted to be just in the Goldilocks zone at the right distance from the star, where the surface is warm enough. You can be farther away, like Enceladus or Europa, and still maintain the chemistry of life. Now, how can you detect that? Well, in the case of Enceladus, the Cassini mission discovered these plumes, geysers, plumes of water vapor emanating from the surface in the form of jets. And in principle, if we fly through these plumes, we can collect water vapor and check the composition and see if there is any signature for molecules that are biological in origin. That was not done because Cassini, we didn't expect, when we designed the mission, we didn't expect those to exist. And a future mission could look into the composition of these plumes and perhaps figure out whether there is life under the ice on Enceladus that we can infer from the composition. We already know that there are organic molecules in these plumes with an atomic number of more than 200. So there are more than 200, protons and neutrons in these molecules that are very large organic molecules, but we don't know if they are indicative of life or not. And so it's quite possible. And then Europa also has hints of such plumes coming off from observations by the Hubble Space Telescope. Now, of course, you can imagine a mission that will land on the surface of Europa and drill through the ice and then put perhaps a fishing net to collect any fish that you find under the ice. So,
well, we call them the European space whales.
Certainly, we could check if there's anything on the surface, that is organic, and so. But that's for the future. It would be extremely exciting. Now we also know that there is a lake on Mars under the surface, most likely, and we could check that for signatures of life. By the way, it's not at all clear that life started on Earth. It could have started on early Mars and transferred to Earth by rocks. We know that some Martian rocks made it. Yeah. And there are animals, including tardigrades, for example. These are microscopic water bears that can survive the harsh environment of space. In fact, a bunch of those was taken to space by a French space mission, and they survived for more than a week and brought back to Earth under dehydration and the extreme conditions of space. And then once they were put in water, more than half of them reproduced healthy embryos. So you could imagine some of these either microbes or tiny animals surviving inside a rock that is launched into space and landing on another planet. So life could have been transferred from Mars to Earth or vice versa. One thing we have to be careful with is, as we visit those places, we should make sure that we don't bring life with us.
One of the ideas that I find really fascinating with this whole idea of this interstellar asteroid, this Oumuamua, somebody did the calculations that at any point there could be 30,000 asteroids like these interstellar asteroids passing through the solar system at any time.
Yes.
And so you can take that whole idea of panspermia and scale it up another notch, which is that there could very well be this transportation of life from solar system to solar system.
So actually, 2 points about that. First, about a decade ago, we wrote, I was involved in a paper, the first paper to estimate how many interstellar objects
of course you were.
should pass through the solar system. And we estimated a number that is 1 million times less abundant than needed to explain Oumuamua. And so, first, that's quite remarkable that we found this object because we didn't expect it. Okay, so theoretically, making analogy with the solar system, assuming that all other stellar planetary systems are similar to the solar system, we infer the rate of incidence that is 1 million times less. But another interesting point is, now that we know that the Oumuamua exists, so we wrote another paper saying, there is a fraction of those objects that pass through the solar system from interstellar space, a fraction of those that get captured. Mm-hmm. Because the Sun and the Jupiter are the biggest objects in the solar system, and they can act as a fishing net to collect such objects. Because if an object passes close enough to Jupiter, it will give Jupiter a little kick, and by that get captured into an orbit. And once you have these bound objects, and there should be thousands of them in the solar system right now, you can visit those. You can design a mission that will land on the surface of these objects and check for any signatures of life. And that is a much more efficient way of figuring out whether other planetary systems around other stars have life. Instead of taking a long journey to visit those stars that could take 100,000 years if we use chemical rockets. Instead of doing that, we save the time because these objects made the journey that took them 100,000 years, and they are now in the solar system. They came from outside, and we can examine them and infer the properties of objects around other stars. And so that opens a completely new way of probing the environments of other stars.
If only there was a way that we could send lots of little spacecraft around the solar system to study each one of these little objects to study it. So perhaps if someone can work on that. Okay, so I want to talk about one last subject that. Well, actually, I've got two. So the next one I'd like to talk about is this idea of protecting against the dark energy future when the acceleration of the cosmos takes away all of our future stuff.
Right.
So you proposed a way to deal with that. And actually another researcher at literally almost the same time, right? Two of you published papers at almost the same time, didn't you, about this?
Well, so it all dates back to the time that the universe, the discovery that the universe is accelerating and that eventually won the Nobel Prize. The discovery was led by two former graduate students of my department. And they realized that the universe is accelerating. And shortly afterwards, I started thinking, what are the implications of that? And the implications are that if you look at distant galaxies, they're receding from us at a speed that increases with time. And eventually they will reach the speed of light. So even light will not be able to bridge the gap that is being opened between us and those sources of light. And so we won't know the whereabouts of those galaxies in the distant future. We won't be able to find out what happens there. And then we will be left on our own in the darkness, in an empty universe, just, the Milky galaxy. And when I wrote that paper, I got an email from Freeman Dyson, who indicated, he said, well, maybe we should engage in a cosmic engineering project. That was about 6 years ago. And in which we will collaborate with other civilizations and perhaps bring ourselves together. And recently, someone actually, and I told him, look, this is too much to ask, to move a star or ourselves together with other stars, bring them together is a huge engineering project. It didn't sound realistic to me. Then there was a paper recently suggesting to move stars around. And that led me to write a response saying that instead of collecting stars and moving them artificially, in fact, nature established already those regions of space where there is a lot of resources. These are called clusters of galaxies. They are the biggest collections of stars in the universe. They have roughly 1,000 times the mass of a single galaxy like the Milky Way. And they were assembled by gravity, naturally. And we don't need to assemble stuff so that it will not run away from us in the distant future. We don't need to assemble these resources, this fuel for the future ourselves. Nature did it for us. All we need to do is propel ourselves into the nearest cluster of galaxies. Now, if I think about the same logic, other civilizations may have already thought about it, and they might be already on their way into clusters of galaxies. So if indeed this is not an original idea, if other civilizations are doing that, there must be traffic of civilization towards clusters of galaxies. As we speak, we can't really see them easily because they're not producing a lot of light relative to stars. It's just spacecrafts moving them in the right direction. But it would be a smart thing to do. And if a lot of those civilizations do the same thing, they will find you will find a large concentration of civilizations in those clusters of galaxies. If we stay within the Milky Way galaxy, like some loners might prefer to do, we might find ourselves in a small environment that doesn't have a lot of resources, and then nothing around it. So I would advocate actually joining the crowd in those big clusters.
We've only got 100 billion stars to work with here in the Milky Way, and that's nothing compared to what we could. And I guess what we'll get from Andromeda when it collides with us, creating Milkdromeda, but but it's nothing compared to the amount that's going to be in those.
It's only a factor of 2. It's only a factor. And the other thing to keep in mind, the sun will burn up, it's roughly at the middle of its life right now, so it will burn up in about 7 billion years or so. It's by no means the longest lived type of star. In fact, it's the least, it's not very common. It's not a star that is very common. The smaller stars are much more common. These are called dwarf stars that have roughly a tenth of the mass of the sun. Proxima Centauri, the nearest star to us, is one of these stars. It has 12% of the mass of the sun, and it would live for 1,000 times longer than the sun. It would live for a few trillion years. And there is another star that is near us of that type. It's called the TRAPPIST-1, and it has 7 planets around it that are known, that 3 of which are habitable. And it has 8% of the mass of the sun, and it would live up to 10 trillion years.
Right.
So these are the longest lived stars, and we will find ourselves next to one of them if we want to be close to a furnace that lasts much longer than the sun.
All we need to do is just tear the sun into 13 equal parts, and we'll be fine.
No, we can just move into those locations.
Right.
Proxima Centauri is the nearest star. We can just go there. And I should say, the habitable planet around Proxima Centauri, that is called Proxima b, is 20 times closer to the star than we are from the sun. And that's the habitable zone because the star is so faint that you need to be much closer to it. And because it's so close, the planet is tidally locked. It shows the same face to the star at all times as it moves around the star. Just like the moon shows us the same face as it moves around the Earth. And so there is a permanent day side and a permanent night side. And my daughter said to me when she heard about it, that if we ever go there, she would like to have 2 houses. One on the permanent night side where she will sleep, and the second one on the permanent sunset strip that separates the day side from the night side, where she would have the vacations. So you have a permanent sunset over there.
Now we've got about 8 minutes left. Your time's very valuable. One question that came up a little while ago, and I know you're involved in this as well, is the Event Horizon Telescope. When do you think we're going to see the first pictures from the telescope? When do we see that first picture of a black hole?
My guess is that within half a year from now, we will see an interesting result from this telescope. The data was already collected. It's high quality data, and it's being analyzed right now. It was taken under very good conditions, so the quality of the data is high. I haven't seen any image or any results yet, but the team is working hard to analyze the data, and I expect it to be exciting within half a year from now. And the idea is to get an image of the shadow of the black hole on the background light that comes from the matter falling onto it. So you can think about this illumination from the background light as being some wallpaper on top of which the black hole sits, and you will see the shadow of the black hole. So you could measure the size of the event horizon. You can test the general relativity, Einstein's theory of gravity, although that was already tested by LIGO, by detecting gravitational waves from the collision of 2 black holes. I should say that, LIGO made the discovery for which the last Nobel Prize was awarded exactly 100 years after Einstein formulated his equations of general relativity. And Einstein himself, so he formulated the equations in 1915, but then around 1935 or so, he started to doubt that gravitational waves exist. And he wrote a paper together with his postdoc, Podolsky, arguing that gravitational waves do not exist, that they have some mathematical singularities that make them some fictitious mathematical objects that do not really exist in nature, that they're not of physical significance. That was a wrong paper, and the reviewer of the paper tried to correct the mistake, and Einstein was very upset that this paper was submitted for review. He thought that it should have been published but actually this reviewer saved him from embarrassment. And then he wrote another paper just a few years later, arguing that black holes do not exist. And his reasoning was that if a star collapses, even if there is a little bit of spin, that will prevent the matter from collecting in the center. And that was also wrong. As we know, stars do collapse and make black holes. And LIGO basically demonstrated both of these to exist, both gravitational waves that were the messenger that provided us with the information about the collision of two black holes in perfect agreement with the equations that Einstein formulated much earlier. And this is an important lesson in the history of science because it shows you that experiments are really essential, that even someone as smart as Einstein could get sometimes things wrong.
Yeah.
And around the same time, he also thought that the quantum mechanics cannot be right in the way it's formulated, must have some underlying physical interpretation that he thought of as being causal and deterministic. And that was wrong as well. And so I think we should stay humble. You know, the pleasure of doing physics is that you can remain a child in your adult life. You can still wonder about the universe, make mistakes, and correct your prejudice based on experiments. And that's wonderful. You know, there aren't many occupations that allow you to make mistakes like that.
I know that we're all really excited about it when that image from the Event Horizon Telescope comes out. But I think you and your team made a bunch of the simulations on what we should expect to see. And I know there's actually been some readings have been done over multiple years. And what would you be surprised to see?
It would be surprising if the shape of the shadow is different from what we expect, because in Einstein's theory of general relativity, irrespective of how fast, how rapidly the black hole is spinning, the image looks pretty much robust to that, insensitive to spin, and it has a characteristic size, and we pretty much know the mass of this black hole. So if we see anything different than what we expect, that would be very interesting. Now, LIGO confirmed the existence of black holes, but seeing is believing. You know, if we see something, there is no reason to suspect that we will not see what we expect, but if we do see, perhaps, there is something else out there. And, some of the most fundamental puzzles we have in present-day physics have to do with the unification of gravity, according to Einstein, with quantum mechanics, which is another pillar of modern astronomy, of modern physics. And there could be surprises that have to do with the way that these two theories are unified. We don't have a theory that marries them in a way that was tested so far. And so by looking at black holes represent one of these extreme environments where we can possibly see deviations from Einstein's theory of gravity.
Well, so we're just going to last a couple of minutes. So, Avi, I just want to thank you so much for taking the time to talk with us today. I know that I could just have these conversations all day long, but you've got some physics to get back to. Where can people find out more about what you're working on?
Well, if they just Google me, Avi Loeb, L-O-E-B, they would find a lot of material in the form of news articles, opinion essays, and also publications, professional publications, on my personal website at Harvard. And I'm also always interested in speaking with people, irrespective of how broad is their education. And in fact, I often find people that are not very educated, people that come to work, for example, in our backyard. I find the discussions with them more fascinating. So I would welcome anyone that wants to speak with me,
especially if it's some idea that maybe someone hasn't done the math on yet, and right. There's an interesting analogy there. That's terrific. And what will we see next? What is the thing that you're working on right now that maybe we're going to see soon? You can be specific.
I'm working on a number of projects. One of them is trying to understand what a singularity of a black hole is. What is this thing that where Einstein's equations break down there? I'm working on a book related to the search for intelligent and primitive life, and there are many new ideas that will be there. And I'm also working on the very first galaxies, the very first stars in the universe, the scientific version of the story of Genesis. These are the main three areas. And, if you ask me any day of the week, I will give you a different answer because, it's a creative process by which there are new ideas that come along and new papers written. And roughly every year I have about 40 papers or so, papers.
Yeah.
And so every couple of weeks there is a new paper, and it's hard to forecast exactly what the next paper. I should just be grateful that I'm not being assigned a job that will take away my free time, and also that I have such a supportive wife and family that allows me to do all of this. And finally, every time I wake up in the morning, I'm worried that maybe I will lose it and not have any new idea. It's never guaranteed,
Well, I from my perspective, I can't imagine that'll ever be a time. And I just want to give you a big thanks from as a journalist, someone who is like trying to report on this kind of stuff and is always looking for interesting ideas that I think is going to ignite the audience and sort of help them with some of their intellectual curiosity. You do such a great job both of generating ideas and writing papers, making them very accessible, but also making yourself really available to those of us who have more questions. So I know that I don't know where you find the time. People say that to me, but you're the person who I have no idea. Literally, I think there's a Nobel Prize because you've already figured out how to bend space-time, and that's how you have found the time to do the work. But thank you so much. I know the audience appreciates you joining us this week, and love some time to talk with you in the future after the next few hundred papers are out.
Thank you. My pleasure.
All right. Thanks, Avi.
Bye-bye.